It all began in the ashes of war when rocket science was still more of a fantasy than a frontier. As World War II raged across continents, a different kind of battle was unfolding in the minds of physicists and engineers: how to escape Earth's grip using fire and fuel. Back then, rockets weren't elegant machines of precision, they were crude, dangerous, and made of experimental parts. But among the chaos emerged a pattern that would shape the next century. The type of fuel you chose could make or break the mission. The earliest rockets, like the German A4, ran on mixtures that sound more like a distillery recipe than advanced propulsion: ethyl alcohol and liquid oxygen. It worked barely. But it was messy, inefficient, and unsustainable, especially for the interplanetary dreams humanity would soon chase. Fast forward to today, and SpaceX has rewritten that fuel story with the creation of Raptor engines, powered not by alcohol or kerosene, but by a far more radical choice: liquid methane. At first glance, that might not seem revolutionary. Methane is the primary component of natural gas. We use it to heat homes, cook food, even generate electricity. But in the context of deep space travel, of sending 100 tons of cargo to Mars and bringing the ship back, it's a game changer. It's not just about lighting a fire and pushing metals skyward. It's about building a fuel ecosystem that can support life and travel millions of miles from Earth without relying on it. That's why SpaceX isn't just launching rockets. It's also building the fuel production systems to go with them, including an air separation unit, or ASU, on Earth that mimics how we'll one day make methane on Mars. But to understand how far we've come, you have to understand how we started. On October 3, 1942, something remarkable happened. A rocket known as the A4 soared above the clouds and into the upper reaches of the atmosphere, becoming the first man-made object to cross the Kármán line, the invisible border between Earth and space. Fueled by ethyl alcohol and liquid oxygen, it represented the birth of true rocketry. The man behind it was Wernher von Braun, a German scientist whose work would eventually power the American Saturn V that sent Apollo astronauts to the moon. But back in the 1940s, his tools were primitive. Germany, strained by war, needed a fuel that was accessible, affordable, and effective. Ethyl alcohol fit the bill. It could be distilled from crops like potatoes, requiring no exotic infrastructure. And when mixed with LOX, liquid oxygen, it ignited cleanly and reliably. The result was a primitive yet functional missile that could reach a peak altitude of 100 kilometers. Of course, there were compromises. Ethanol wasn't especially efficient. Its specific impulse, a measure of how much push you get per kilogram of fuel, was just around 250 seconds. That meant it took a lot of fuel to get relatively little force. But during wartime, simplicity won over sophistication. There were other options like kerosene, but in the 1940s, kerosene hadn't yet been refined into RP-1, the clean-burning high-energy rocket fuel we use today. And while hydrogen offered incredible efficiency, its storage challenges were nearly insurmountable with the technology of the era. Hydrogen had to be kept at temperatures near absolute zero, and required cryogenic insulation well beyond what engineers could safely manage in combat environments. Alcohol, by contrast, was familiar, safe to store, and ready to scale. After the war, the Allies saw the potential in von Braun's designs and brought his team to the United States. There, the rocket revolution truly began. Engineers wanted more power, higher altitudes, greater payloads. That meant leaving behind alcohol and embracing something with more energy. RP-1, refined petroleum-1 or rocket-grade kerosene, became the backbone of American and Soviet rocketry. It was denser than ethanol, easier to store than hydrogen, and packed a bigger punch. Rockets like the Redstone, Atlas, and R-7 all used it, and eventually so did the mighty Saturn I and the Falcon 9. RP-1 offered a specific impulse closer to 310 seconds, a sizable leap from ethanol's 250. That difference allowed engineers to build smaller fuel tanks, lighter stages, and carry heavier payloads. It was practical, cheap, and well understood. And for decades it was more than good enough. But space has changed. No longer are we simply sending satellites into orbit or astronauts to a nearby station. Now we're preparing to build on the moon, terraform Mars, and settle worlds that exist entirely outside Earth's supply chain. In that context, RP-1 begins to show its flaws. It can't be synthesized easily off-world. It leaves behind carbon residues that foul engines after repeated use. And it doesn't offer the same level of performance you'd need for both launch and return journeys. That's where methane steps in. Liquid methane offers the perfect middle ground between RP-1 and liquid hydrogen. It has better energy density than hydrogen, making tanks smaller and lighter. But unlike RP-1, methane burns clean. Its exhaust leaves virtually no soot, which is critical for a fully reusable engine like the Raptor. When SpaceX lands Starship and prepares it for another mission, it can't afford to scrub carbon deposits off turbine blades and nozzles. Every extra hour of maintenance costs money, delays flights, and adds risk. Methane avoids that. More importantly, methane can be made on Mars. And that changes everything. The Martian atmosphere is rich in carbon dioxide. The surface contains buried water ice. Using a process known as the Sabatier reaction, CO2 and H2O can be converted into CH4, methane, and O2, the very same propellants that Starship's Raptor engines use. This means future astronauts won't have to carry return fuel all the way from Earth. They'll be able to land, mine the ice, extract carbon from the air, and produce their own fuel on site. It's not science fiction. SpaceX is already laying the groundwork with Earth-based fuel production prototypes. The ASU, Air Separation Unit, approved by regulatory authorities, is designed to capture carbon from the atmosphere and turn it into methane, just like we do on Mars. This isn't just a test of equipment, it's a rehearsal for off-world survival. Compared to liquid hydrogen, methane is far easier to work with. Hydrogen molecules are tiny and tend to leak through even the best seals and containers. It also needs to be cooled to just 20 Kelvin, an extreme engineering challenge. Methane, on the other hand, stays liquid at a relatively manageable 111 Kelvin. That translates to easier storage, cheaper insulation, and less risk of leaks. And while hydrogen is more efficient in a vacuum, the overall trade-off tips in methane's favor for missions that involve landing, relaunching, and long-term storage. There's also the reusability factor. A big part of SpaceX's vision for Starship isn't just reaching orbit or Mars, it's making it routine. That means rapid reusability. Imagine a rocket that can land, refuel, and fly again in hours, not months. RP-1 engines struggle with that due to carbon buildup and thermal cycling stress. Hydrogen engines like the RS-25 from the Space Shuttle era are incredibly complex and expensive. Raptor, burning methane, is designed to be robust, simple, and easy to refurbish. Its full-flow staged combustion cycle pushes hot gases through both oxidizer and fuel turbines, improving efficiency and reducing wear. That kind of design, when paired with a clean-burning fuel like methane, means an engine that can fire again and again with minimal downtime. So while the early rocket pioneers were working with what they had, potatoes turned to alcohol, and whatever oxidizer they could stabilize, SpaceX is building a future where fuel isn't a bottleneck but a bridge. From the fields of Germany to the icy plains of Mars, the story of rocket fuel is one of adaptation, innovation, and a relentless pursuit of better. And in that story, methane isn't just a new fuel. It's the first real step toward making space travel sustainable, affordable, and eventually, normal. Because to go to Mars and stay there, we don't just need powerful rockets. We need the right kind of fire. Starship isn't just a rocket, it's an engine of change. Towering nearly 400 feet tall, fully loaded with over 5,000 metric tons of fuel, and yet somehow engineered to weigh just under 290 tons when dry, Starship achieves something few vehicles ever have: extreme size with incredible efficiency. That dry mass is only about 5.8% of its total liftoff weight. For comparison, that's like a semi-truck carrying an entire freight train on its back and still managing to coast uphill. In the world of rocketry, that ratio is a masterpiece. It reflects not just the raw physics behind escape velocity but also a deep understanding of engineering, material science, and propulsion chemistry. The reason Starship needs so much propellant is simple. Overcoming gravity is brutally hard. Getting through Earth's thick lower atmosphere and reaching orbital velocity demands staggering amounts of thrust. And the only way to create that thrust is through burning fuel. A lot of it. But it's not just about filling tanks. The quantity of fuel alone doesn't determine success. It's about how efficiently that fuel is used. That's where a rocket's specific impulse, measured in seconds, becomes critical. Think of it like miles per gallon in your car. It measures how effectively an engine converts propellant into thrust over time. A higher specific impulse means a rocket can go farther, carry more, or burn fuel for longer. That's a huge deal when you're not just trying to escape Earth, but land on the Moon, survive on Mars, or return again. RP-1, the refined kerosene fuel used in rockets like Falcon 9, delivers a specific impulse of around 300 seconds in a vacuum. That's solid, reliable, and proven. But liquid methane, the fuel used in Starship's Raptor engines, can reach around 380 seconds. That's a full 80 seconds more performance in space. Over a long mission, that margin can make or break success. That 25% gain can be the difference between crashing back to Earth and safely landing on another planet. Imagine two identical rockets. One is powered by RP-1, the other by methane. They both launch from the same pad with the same fuel mass. As they ascend into the vacuum of space, the RP-1 rocket might barely make it past the moon. But the methane-powered Starship could make the full journey, land safely, and still have enough propellant to begin preparing for the trip home. That's not theory, it's physics. That's the hidden math behind SpaceX's choice. And yet, if efficiency was the only concern, why stop at methane? After all, liquid hydrogen offers the highest specific impulse of any known fuel, up to 465 seconds in a vacuum. That's nearly 100 seconds more than methane. So why didn't SpaceX go all the way? The answer is elegant, grounded, and Martian. Hydrogen is a beautiful fuel on paper. It's light, it's powerful, and it produces only water vapor when burned with oxygen. But in reality, it's an absolute nightmare to work with, especially on a planet like Mars. Hydrogen is incredibly cold, requiring storage at -253 degrees Celsius. That's just 20 degrees above absolute zero. At those temperatures, everything becomes fragile. Seals crack, pipes shrink, metals behave unpredictably. And hydrogen is the smallest molecule in the universe. It seeps through microscopic cracks. It escapes containment. It corrodes metal over time. It turns straightforward engineering into a never-ending battle with thermodynamics. On Earth, you can brute force your way through that challenge with energy and infrastructure. But on Mars, where power is limited, maintenance is dangerous, and every gram counts, those complexities can become mission-ending. Methane, by contrast, is the practical engineer's dream. It only needs to be chilled to -161 degrees Celsius, still cryogenic, but vastly more manageable. It's easier to contain, evaporates more slowly, and doesn't leak through seals. And crucially, you can make it directly on Mars. Thanks to a century-old process called the Sabatier reaction, carbon dioxide from the Martian atmosphere can be combined with hydrogen from local water ice to produce methane and oxygen, both of which power the Raptor engines. That's not science fiction, it's basic chemistry. Mars has abundant CO2, making up 95% of its thin atmosphere. And subsurface ice has already been confirmed in multiple regions. Future missions can mine the ice, extract the hydrogen, and synthesize the fuel needed to return to Earth. That means Starship could not only land on Mars, it could refuel there too. That's the heart of SpaceX's long-term vision, a closed-loop supply chain between planets. Methane is the only fuel that makes that vision possible. Even the thermal properties of methane align beautifully with the mission. When it burns, methane reaches temperatures around 3,277 degrees Celsius. That's cooler than RP-1, which burns at nearly 3,400 degrees and puts intense stress on engine components. Methane's cooler combustion helps extend engine life, especially when reuse is the goal. Hydrogen burns even cooler, around 3,000 degrees, but again, its handling complexity outweighs that benefit in most scenarios. Raptor engines, burning methane, strike a balance: high performance, manageable heat, and clean combustion with minimal residue. That matters when you're trying to build a rocket that can fly not once a year but once a week. And then there's storage. Fuel tanks are one of the heaviest parts of any rocket. Keeping cryogenic liquid stable without constant boil-off requires powerful insulation. The higher the boiling point, the easier it is to maintain the fuel in liquid form. Methane's relatively high boiling point, compared to hydrogen, means less insulation is needed, which directly translates to lighter tanks and simpler designs. Even better, methane and liquid oxygen have similar storage temperatures. That allows engineers to place them in adjacent tanks, separated by a common bulkhead. This saves mass, reduces complexity, and simplifies refueling systems. By contrast, hydrogen and LOX have wildly different temperatures, making it dangerous and inefficient to store them side by side. Hydrogen could freeze the oxygen, or the oxygen could vaporize the hydrogen. It's a dance that requires constant management, something Starship deliberately avoids. To support this entire architecture, SpaceX is doing something almost unheard of in aerospace, building its own oxidizer production plant from the ground up. In Cameron County, Texas, just 300 feet from the rolling sand dunes of Boca Chica, SpaceX has been granted approval to construct a new air separation unit, or ASU. This small but powerful facility will act like a miniature refinery, drawing in atmospheric air and distilling it into its most useful components: liquid oxygen and liquid nitrogen. LOX is the oxidizer that burns with methane in the Raptor engines. LN2, or liquid nitrogen, is used for cooling systems, engine testing, and pressure control. Right now, SpaceX needs over 200 tanker trucks of these cryogenic fluids for every Starship launch. Each delivery clogs Highway 4, creates noise, and adds nearly $1 million to each flight's price tag. That's not sustainable. The ASU will change that. Covering just 1.66 acres, about the size of 1¼ football fields, the facility will house 20 major structures, including a 47-meter tower that stretches nearly 15 stories high. Despite its small footprint, it will punch far above its weight. Medium-sized ASUs can produce between 150 and 1,000 tons of liquid oxygen per day. Even a modest 500-ton output would equate to over 438,000 liters daily. That's enough oxidizer for multiple launches per week. It's fast, it's local, and it puts control directly into SpaceX's hands. But there's a catch. While the plan sounds revolutionary, it's not guaranteed. The main limiting factor isn't technology, it's electricity. Producing liquid oxygen is energy-intensive. Compressing and cooling air to cryogenic levels requires megawatts of stable, on-demand power. And at the moment, Starbase doesn't have enough of it. Without a dedicated power supply, possibly from solar fields, natural gas, or nuclear, SpaceX might have to delay or even cancel the ASU project. That would mean continuing to rely on external suppliers, with all the cost and inefficiencies that come with them. Still, the ambition is clear. Starship isn't just a launch vehicle. It's an integrated system, propulsion, fuel production, logistics, and reuse, wrapped into one monumental spacecraft. The choice of methane over RP-1 or hydrogen isn't arbitrary. It reflects a future where rockets don't just launch, they live, they refuel, they return. They do it again and again until going to space is as normal as crossing an ocean. That's the dream. And methane is the flame that could make it real.